Hey everybody, welcome back. It's Jonathan Templin again from Clemson University. This time I'm talking about generalized linear models. I'll make it a little bit more specific. This lecture is really about logistic regression, but I'm trying to frame it in the context of a broader picture. And really the idea is what happens when you have data, an outcome variable that is not continuous and is not plausibly normal or conditionally normal, where you can't just stick it into a linear model where you have that normal error term. So stay tuned or buckle up. And because this is YouTube, don't forget to hit like and subscribe. Smash that bell if you want to hear the bad jokes continue. Let's go. In this lecture, we're going to talk about taking what you know about linear models and expanding it to outcomes that are not potentially conditionally normally distributed. Remember, y in a linear model isn't necessarily normally distributed, but error is. And we like to say that y has to be plausibly continuous to really go about using that model. We're going to frame what we know about those in the context of a little bit larger, a generalized linear model context, where we could use many different distributions to model outcomes that aren't just nicely fitting into this continuous symmetric mode that you nicely would normally see. We're also going to further our ideas and knowledge of maximum likelihood because the building blocks of maximum likelihood enable us to really understand distributions, that is, really understand how we can model things with different types of data. And to wrap this up, I will show this in the context, again, of logistic regression, which is a generalized linear model for an outcome, in this case, an outcome variable that takes two values, a 0 or a 1. We will have to put that into a distribution for that outcome, a Bernoulli distribution. And we'll have to talk about modeling the mean of the distribution, which will actually be a probability. So going between 0 and 1. So we need to convert that probability into something that is continuous to allow it for predictors like we would have in a linear regression. Okay, diving in. Statistical models can broadly generalized, at least models for prediction, can be broadly generalized or organized like this. General linear models, which are conditionally normal outcomes, versus generalized, right? And really, in this case, is not necessarily a normal distribution for that outcome. We could also characterize these as one-dimensional of sampling, like, for instance, one variance per term per outcome, versus potentially multiple dimensions of sampling, like in a multi-level model, right? Multiple variance terms themselves. And this is where the distinction between fixed effects versus mixed models shows up, the fixed and random effects that you'd see like in a multi-level model. Now, all models will have fixed effects, but then general linear models are conditionally normal distribution for the data, right? The data are normal conditional on all the predictors. They have fixed effects and no random effects. If we add random effects to those general linear models, we get general linear mixed models, GLMMs, also known as mixed models, mixed effects models, variance components models, etc. These are models with conditionally normal distribution for the data, but both fixed and random effects of parameters. And those random effects typically have more than one variance term. Let me add more than one variance term to the model itself. So you may have a random intercept that has a random intercept variance that represents another dimension of sampling. For instance, students nested in classroom, they would have an overall error variance, a level 1 variance that we would normally think of as our normal term, but you also may have a variance of classes across that intercept itself. Then, going a step further, if we can't claim our data are conditionally normal, so for instance, maybe they're discrete outcomes, right? There's no way a discrete outcome could really be normal. We use something called a generalized linear model, right? Where we have a conditional distribution for data, but it's any distribution. Right? So we could pick a distribution, even ones we've never heard of before. And believe me, there are a lot that we've never heard of, and build a model into it for that data. The fixed effects are in the model again, but now they get the model itself, how we predict it. We're actually making a model for the mean of our outcome, which is what we did in linear models also. But that mean has to go through something called a link function to allow it to be converted from its space of the data, like that probability between 0 and 1, onto the real number line itself, where our fixed effects do our modeling. Right? The generalized linear models don't have random effects. The generalized linear mixed models do have random effects. We're not going to talk about mixed models in this context in this classroom, but as you go further, you may, and that's where they show up. We will talk about general linear mixed models later on in this class as well. Okay, So the idea of linear here actually refers to the link transform portion. So once we take our mean, for instance, a probability, and we convert it to some number that ranges between negative infinity and positive infinity, then we put a linear model on that converted mean itself. Now, let me make a distinction as we go further. We are not transforming our data. In fact, these models exist so we don't transform our data. Right? If you have data that don't quite fit the assumptions of a model, what we're saying is change the model. Don't change the data. Because if you change the data, you may change the effects that you're after, and therefore you may end up making arbitrary decisions that impact your results, your conclusions, your answers to your research questions. So no, change the model, and these are the tools by which you can do the change. So the big picture is this. If we think of equation, y equals beta 0 plus beta 1 x plus error over here, right? If you had a hypothesis, some type of substantive model theory, that shows up on the right hand side of a linear model. And we're saying that if we had believed this to be like a causal process, perhaps that would cause the outcome itself. And maybe not entirely, so we may have error there. So this same idea holds in generalized models. The right-hand side, your theory stays the same, but the mapping on the left-hand side changes because the data themselves may not be continuous. Right? So we have to think about ways that we can go model things that are not just continuous. We have continuous variables, time, blood pressure, height. We may have categorical variables like Likert type item responses or ordered categories. Maybe, how much did you like our service between 1 and 5 or something like that. Or nominal categories, right? Which one of these outcomes would you pick? Maybe there's no ordering to them. You could even have count variables in there. How many times did you smoke a cigarette yesterday or something along those lines? Finally, we could have combinations of continuous and categorical variables, right? A fixed discrete 0 and some other continuous number. I like to think of this one in the context of, have you ever taken a survey with a slider bar? Right here, right? Maybe show us your opinion. 0 is disagree, 100 is totally agree, and there's some type of slider that you have to move. Well, this is continuous in this range, but if a person moves the slider all the way over to the end, that is a very discrete endpoint as well. Each of these types of situations can be modeled with a linear model preserving our substantive theory, but the only difference is we have to pick the right distribution on the left-hand side, because when we pick that distribution, right, to mirror the sample space of our data, now then we have to think about its mean and a transformation of its mean. Now, I keep talking about its mean, and for this class, we'll only talk about the mean of the distribution. There are broader models out there that allow you to do modeling of not just the mean, modeling of the variance, and those follow other terms, heteroscedastic variance models or location scale models, or if you really want to put all of them together, mixed effect location scale models. Don Hedeker's work, also important there. Lisa Hoffman's written a few papers on that. This is just the beginning of the rabbit hole to go down, but it's a great rabbit hole, and I'm looking forward to leading you down this crazy journey. It's kind of like Alice in Wonderland, maybe. Here we go. All right. The goal of generalized models is to map your substantive theory onto the sample space of your outcomes. Remember that term sample space, right? That's the range of outcomes that are possible, right? We have our theory about how the world should work. It's just our outcome data. It just happened to be the form that they come in, right? So what we want to do is change the model, not change the data. So the general idea is that the statistical model will not approximate the outcome well if the assumed distribution doesn't fit the sample space of our outcome. Right? So if the model doesn't fit the outcome, we can't believe the findings. The key to making all this work is the use of differing statistical distributions for the outcome. This is why I was teaching about distributions previously, because I want you to know that other distributions exist. And this choice of, in modern statistical language, in modern data science, is we don't just shove our data into some old distribution because that's what works. We can build our own process around a distribution that better fits our data. And generalized models are the types of tricks to do this. They allow for different distributions for outcomes. The mean of that distribution is still modeled by the model for the means, and the variance of the distribution may or may not be modeled, depending on whether or not that distribution has a variance term or not. And we're going to see that really quickly, because when we work with binary data and we use a Bernoulli distribution, which we'll introduce in just a bit, it doesn't have an error term. It has one parameter. In fact, it doesn't have a variance term. The mean, that probability, right? The mean has to range between 0 and 1. If the value of the distribution can be only 0 or 1, its mean has to be between that. The variance turns out to be the mean times 1's minus the mean. So, what type of outcomes? There's a difference between generalized versus general, right? General linear models are models whose residuals follow some not normal distribution. Sorry, generalized, this should be right here. Actually, no, this is the definition. Read the slide, Jonathan. Generalized linear models take general linear models and add residuals that follow some type of not normal distribution, and in which we have to use this linked function to transform the mean of y itself. So for instance, there are many different types of outcomes that we might want to use this for. Binary data, like we're going to see today, unordered categories, ordered categories. Sometimes they fall under multinomial. You may have counts. Distributions show up in counts include Poisson or negative binomial. You may have censored distributions. You may have zero inflated distributions where you have a big pile of people at zero. You may have continuous but skewed data. Right? There's all sorts of ways that we can do this. Pretty much any distribution is fair game. And here is from the distributions, there's the name of distributions, where we might use them, and the function that transforms the mean itself for each. And this is really what I want to focus on. Today, we're going to be working in this Bernoulli distribution right here. And the reason why it's called logistic regression, because this thing that I'm going to explain in a few more slides takes the mean of our data and transforms it using this function where the mean divided by 1 minus mean. Inside of there, that's called the odds. And we apply the log of the odds. It's a natural log right there. And we end up getting a logit. That's the result of all this on the right-hand side is something called a logit. And that's where the word logistic regression comes from. But again, you can see with all of these distributions, see, this is a Wikipedia page describing them. Each one of them has some type of link function, has some function of the mean itself. And on the right-hand side over here, the very far right, this is going from our model back to the mean. Right? So our model goes that the term inside those parentheses is in logits. We want to convert that back into probabilities. We can. Right? So this is how we get the models to work, and it can be exceedingly complex. It can also be very straightforward. So this is sort of how we go. Turns out we were already using, if we were thinking of linear models like linear regression, analysis, variance, etc., that is a generalized model of sorts, because what we call that is a model with an identity link function, meaning the mean is the mean. We don't have to transform it. I bet you didn't know that. It's mathematical. We just multiply it by 1. Sometimes we call 1 the identity. That's why it's called the identity link function. Right? So the model for the means, or the structural model, is how predictors linear relate to the link transform outcome, or mean. Right? So here we still have our linear model, and the model for the variance talks about errors themselves. So generalized models work by providing a mapping of the theoretical portion of the model, right? The right-hand side of that equation I started with, the sample space of the outcome, the left-hand side of the equation. And this mapping feature is done by a link function, right? This link function is a nonlinear function that takes the linear model predictors and all the random and latent terms and constants and puts them onto the space of the mean of the outcome of the variables, right? It's really the mean in this case because we're transforming the mean. Right? Link functions are typically expressed for the mean of the outcome, and we're only going to focus on that. But I mentioned before, you can do the variance. Heck, you can do almost any type of version of a parameter and do the same work for it. So in practice, let's put this into practice a little bit. The link function expresses the conditional value of the mean of the outcome, right? So here, the expected value of y, sometimes we thought about it as y hat. In that Wikipedia slide, you saw that as the mean of y. But remember, this is the mean of y conditional on all the predictors. And what we're going to apply to it is this function, mathematical function g, a link function, right? Or to map our parameters on. So we go from mean to logit by using a g, but we can go from logit back to mean by using the inverse of it. So we can always flip back and forth. And the way we like to see this is the mean itself could be equal to the inverse length function of all of our predictors, right? Whereas the g of the mean here, applying the length function straight to the mean, is where we put our linear model itself. Now this term, the linear model, sometimes gets referred to as the linear predictor, the linear portion of the generalized linear model itself, right? And the values are linear combinations. This is the fixed effects model. In fact, these are the same notation I've used when I introduced linear models in this class. Now, we can use normal. Now, the normal model, again, we had the identity link function. This is exactly what I was saying. There's two parameters in the normal distribution, the mean and the variance. Turns out we were already modeling the mean. That's why we call this the model for the means. So really, the model for the means is just the number one, or the inverse link is just number one times that right there. So it's kind of a silly distinction. So I'm not going to really dwell on it. Now the variance is kind of interesting. We could actually come up with a model for the variance itself if we really wanted to. But this is, remember, the variance, the algebra of expectations. If we said, what does our model predict about our data, what the variance should be? If we plug our model in, remember, everything that's not a random variable goes away, leaving us just with the variance of error, which by definition is sigma squared. And we're going to quickly see that in our binary data, we're not going to have this variance of error. We're not going to have a sigma squared in our data. It's kind of weird to think about, but it is very much there. Okay, let's dive in with a concrete example. The hard part about teaching these models is that when we talk about link functions, we kind of get ahead. The theory gets so far ahead of where the data is. It's really hard to make sense of it. Let's get back to data and try to make sense of it. For data, that sprinkling in of theory is for you. If you are going further in this and you have data that needs a generalized type of model, I'm hoping that these slides will give you a head start on where to find that information. Okay, I'm going to use a data example from the UCLA website for ordered logistic regression. The data come from a survey of 400 college juniors looking at factors that influence the decision to apply to graduate school. And since this is a course for graduate students, you have all made that decision and you're all here. Welcome. Great. Probably remember what it feels like. Heck, I even remember what it felt like. Okay, how do we do this? Well, we take our outcome variable y, and that is the student rating of the likelihood that he or she will apply to grad school. And it's kind of a three-part scale, although I'm going to cut this down just because of I want to keep this somewhat simple. Remember, this is not something to do with your data. This is didactic purposes. We would normally keep this as three categories, but three categories complicates it more than I want to put in this survey lecture, intro lecture, what we're doing today. So we're really going to say someone was either unlikely or somewhat or very likely to go to grad school. So if they're unlikely to go to grad school, it's 0. Otherwise, it's a 1. And that's our outcome variable. And then we're going to predict it with whether or not one or more of their parents has a graduate degree, whether or not a student is attending a public university, and their grade point average on a 4-point scale where 4 represents perfect grades. So here are our data. You can see that our GPA variable has a mean of about 300. The likelihood of applying, 55% said likely not to, and then 45% said maybe or definitely likely. And you can see the parent graduate degree, about 15% of the sample had at least one parent with a graduate degree, and about 15% of the sample attended the public university. So this would be very heavily private school students themselves. So let's just think about how this might work if you put that binary outcome into a regular linear regression, right? If y is a binary outcome, then the expected mean is a proportion of people of a 1, right? So it has to range between 0 and 1. The probability of having a 1 is what we're trying to predict for each person. And so the general linear model, again, not the right model, would look like this. Probability for a person is equal to whether or not they, the predictors here, right? Whether or not they have a parent that went to school and whether they're in public college. Its GPA is not in this one. But beta 0 still represents the expected probabilities when all predictors are 0. Each of the betas is the change in that probability for 1 unit change in the predictor. And error would be what's left over, right? Pretty familiar with that. But if y is binary, error can only be one of two things, right? It's either 0 minus that predicted probability or 1, meaning that the mean of errors still has to be 0. But the variance can't possibly be constants over levels of x like we assume in general linear models because the mean and variance are dependent, right? In short, the mean is p and the variance is p times 1 minus p. So they're tied together. That means the conditional mean of y is dependent on x, and so is the error variance. And so what we really need to think about is this. If we plugged our probability into a linear regression, we put a linear line through it, we'll quickly get values that are outside the range of probabilities. Oh yeah, this student has a 1.2 probability of ascending grad school. It's like they're so certain to do it, it almost like gives you probability extra, right? Or heck, the probability that person attends grad school is negative 0.2. Wow, that's really low. That doesn't make any sense, right? A negative probability, a 1.2 probability, things you don't want to see in data, right? Instead, what we really want is this nonlinear function, this S-shaped curve, where as the predictor goes up, we start to asymptote at 1. We find an asymptote, whereas the predictor goes down, we find a lower asymptote at 0. Right? It stays in bounds. And that's what the link function will do for us. So there are lots of problems with general linear models predicting binary outcomes. Maybe not 99 problems. I can think of 3. They have a restricted range. Right? Predictors should not be linear related to the observed outcome. They have to sort of shut off at some point. The variance is dependent on the mean. And also residuals have a limited number of possible values. So instead, we're going to switch the distribution. And it turns out there is a distribution that we use. It's called the Bernoulli distribution. So for items that are binary, right? So the 2 categories that are either values 0 or 1, the distribution we often use is this Bernoulli, right? The notation is this. Our y is a random variable, follows or is independently and identically distributed as a Bernoulli distribution. So we use a B, where P is the probability, is the conditional probability of a 1 for a person P. Now I'm defining this as the probability of a 1, a success. If you're familiar with the binomial distribution, where we might say how many numbers of, we have, let's say we're rolling a die and we're saying the number of ones that we see out of 5 rolls. A Bernoulli is a 1 trial binomial, right? So in this case, that's it. Excuse my notation. I really shouldn't have P sub P there, but that's probability P for person P. I was trying to avoid, commonly in Bernoulli, that mean is denoted as the character pi. So it would be pi sub P, but pi also has a literal number, 3.14, or whatever approximates it. Not going to work. So P sub P is what I got. Sorry. The sample space. Now, our outcome is binary, so we either see a 0 or a 1. That's in set notation here. Right? And when we put that together, the probability density function, or probability mass function, because it's a discrete distribution, is p to the y times 1 minus p to the 1 minus y. So think of it this way. If y was a 1, this part goes away right here. And that part going away allows us to say, the likelihood is probability. If y were a 0, now I can't undo what I just did. Come on, PowerPoint, not going to help me there. All right. Try it again. If y is a 0, what's the probability of 0? Well, it's 1 minus the probability of a 1. That's what shows up. There you have it. All right. The expected value of this distribution is its parameter, p, but the variance is a function of it, right? So expected value, the mean of the Bernoulli is that probability. That makes sense. That's what a mean should be. If all the values were 0 and 1, you can think of the sample mean, the sum of x over n, sum of y in this case over n, somewhere between 0 and 1. That's its probability. The variance of this is the mean times 1 minus the mean, p times 1 minus p. So there's only one parameter. So we only need one link function, and we need a link function to take this thing that goes between, so p sub p, we would say exists in the space 0 to 1, right there. So we need to make that unbounded. We need to put that onto the real number line so that we can model it in a linear model sense. So rather than modeling the probability of 1 directly, we have to make it into more continuous. So we use this link function, right? So One way of doing that, we could form an odds ratio. We could take the mean over 1 minus the mean, but that odds ratio goes from 0 to positive infinity, so that's not exactly going to work. So what we end up doing is taking the natural log of the odds. So log of odds right there. That turns all the values, so that when we apply a natural log, look at this number line here. The odds go from 0, put the number 1 there, and up here is infinity, right? So this is the range, right? The odds of 1 means equal odds of an event happening or not happening, or probability of 0.5. When we take this natural log, it takes all the numbers here and maps them, and this is where I'm going to go negative infinity there, making a semi-number line here, right here. But this whole set of numbers here get mapped onto negative numbers. The log of 1 is exactly 0, and everything in this range above 1 becomes positive numbers. That is what we call a logit, or log odds. Right? There are other link functions, though. Turns out we could use a probit, which is like a cumulative normal distribution. You may hear things like a log-log or complementary log-log. There's quite a few different link functions, but logit is fundamental. It actually has the word canonical that has a statistical definition that I'll just leave for you to be curious about and go find out why it's called that. Log gives logit gives rise to the word logistic regression. So we're just going to focus on that for today. Where I would say you would probably get probit pretty quickly because that shows up in quite a number of other places. It also is the basis for some types of modeling where we have to use something called data augmentation or in a Bayesian sense as well too. All right, this is the mapping I was just showing you from probability onto, actually this is probability onto logit, right? So the probability of 0.5 gives us a logit of 0. And if you want to think about a probability of 0.95, the logit for that is 3. Now the complement of that, 1 minus 0.95 over here is actually negative 3. So this shows you how logits are. They're somewhat symmetric about 0, reflected about 0, excuse me. But as you see, the higher the probability gets, the logit doesn't change much, right? So if you end up getting 0.99999, et cetera, your logit's still going to be, 4 point something or other. Similarly, if you get a probability very, very, very small, the logit's still not going to get very much further below negative 5. Now, logit is infinite on a scale, so you have to get lots of decimal places to get close to where infinity might be on either side of the probability. Now we can transform probabilities into logits similarly, right? So here, a logit of 0 gives the probability of 0.5, or a logit of 0.5 right here. We just said the symmetry about it. A logit of 2.2 gives a probability of 9, so that means negative 2.2 should give a probability of 0.1, the complement. So the question is this: if a logit of 4.6 gives rise to a probability of 0.99, what would a probability of 0.01 be, the complement of that? Well, it should be negative 4.6 right there. Okay, so now we've defined our logit. Let's build that into a link function. So in the terminology of generalized models, the link function is a logit, for a logit, is defined as this right here. So this is the math part, the theory part, but really that's the log of the probability y equals 1 over 1 minus the probability y equals 1. And to this thing, this logit thing, we put our linear predictor. So we are predicting logits now. Now, if you're like, I don't understand logits, you're among good company. It's very hard to think in logits, but we can transform the logit back. This is the beginning of the algebra for it. Lots of algebra, yeah, whatever, blah, blah, blah. We end up with this form here. E to the logit over 1 plus e to the logit. That is a very common way of looking at what we call the inverse link function, right? Going from logits back to probabilities. That is how it works. This e over 1 plus e term, like that, that thing can show up in many different forms, but it's very common that you see it that way. Here's another form of that. 1 over 1 plus e to the negative logit also shows up. It's equivalent. And here's yet another way as well, too. So depending on where you may see this and sort of the level to which they're teaching or the audience to which they're teaching, you may see this in different functions. Like for instance, if you're doing this mathematically, this one tends to be a little bit easier to work with in terms of calculus. If you have to take derivatives of this, we're not going to be doing derivatives in this class. Our inverse link function looks like this, but all three of these are equivalent, and you may see those. So what the link function does is it turns off the prediction. So here, remember, this is our where we don't want it to go above 1 or below 0. It bends the line to have an upper and lower asymptote, right? So the prediction line, upper asymptote is 1, the lower asymptote is 0, exactly where it needs to be. So interestingly, when we predict, if this plot right here is in logits, so I shouldn't have put a 1 and 0 there, but in logits, the prediction in logits, if our y-axis was just the logit itself, it would be linear. But when we convert it back from logits to probabilities, it bends the line. It becomes nonlinear. So our model is linear with respect to the logit, but nonlinear with respect to probability. That is why we call these generalized linear models, because they're linear models for the generalized logit or the link transform part of the mean itself. The logit of the model will be easier to explain. The probability of the version of the prediction will be easier to show, though, right? So we can explain our phenomena in logits, but our impact often goes in probabilities. So we need both of these to sort of back translate our results to people who want to understand what we're trying to do. Now, let's put it together. Let's build an empty model. Under the general linear model, our empty model looked like this. There is y equals an intercept plus some error. Again, we don't have error here. But for the logit, think of it this way. On the left-hand side, it's not y. It's now the logit of the mean of y, right there. And we're going to give it beta 0. Now you'll see there's no error listed there. And that's because error in our regular sense used to have a parameter to it. We don't have a second parameter. We only have a mean. And we're modeling the mean, so it doesn't show up. So if we want to go from probability to our linear predictor, we use a logit. But to go back to probability, if we want to say, what does this logit mean in terms of probabilities? It's right here, e to that value over 1 plus e to that value. But in both cases, the variance of the outcome is that probability times 1 minus that probability. Right? Most linear models, generalized linear models, GLMs, don't list this error term in the linear predictor. It's for the expected value, and error typically has mean, so it disappears. But sometimes you do see it listed, particularly in multi-level models where we actually have to think of its variance. And it's really funny. If you throw an E on there, yeah, technically there may be an E there, but it actually follows a logistic distribution with a mean of 0 and a scaled variance of 3.29, which is really equivalent to the constant pi squared over 3. Let's not talk about this much more. Just know that in some cases, you may see pi squared over 3 or 3.29. That's where it comes from. Let's do this in R then. I'm using the ordinal package. There are many other packages. In fact, there's a built-in package called GLM in R. That GLM package uses iteratively reweighted least squares. I'm using the CLM function because it fits maximum likelihood. The difference is they're equivalent estimation methods, but because we're focusing on maximum likelihood, I'm going to keep working on it in the maximum likelihood sense. But the CLM function is the cumulative linear model function. Here, the syntax that we're going to use is only slightly different from our LM syntax, right? So what we're going to do is our response data has to be a factor. So we take our lapply, that's the 0 or 1. 0 meaning they're not likely to apply, 1 meaning they're likely to apply to grad school. We turn it into a factor, so the levels for the factor will be 0 and 1. And now that is in the CLM function. After the formula statement, that's where it goes. Just like in the LM function in R, we'd have a formula. Lapply tilde 1 means we want an empty model. We give it our data set. We can tell it trace of 1 here to mean we're modeling the probability of 1 itself. And we can get our summary out of it as well. Okay. This control argument, this thing actually is only used to show the iteration history. So I'm tying this to what I taught you about maximum likelihood with it. All right, so the output of the model here is our estimation history. And here's what we get. The empty model for estimating beta 0. Actually, in this case, we're actually modeling the probability of a 0, then a 1. That's really saying our this value should be multiplied by -1 for it to be an intercept. So it's actually called a threshold. Why it's called a threshold, I'll leave for another time. But its value is 0.2007. So our intercept for it was -0.2007, and we still have our standard error for it. So this is interpreted as the linear predictor of y sub p equals 1 for an individual when all predictors are 0. But it's an empty model, so it's sort of our average logit for the sample. And if you want to get back to what the sample mean is, we plug that into e to that value over 1 plus e to the value, the inverse link function, and we get a result of 0.55. That is our sample mean. If you go back to our original data descriptive statistics, we saw that 55% of our sample had a 1 there. The log likelihood for this model is estimated to be right here, -275.26. We can use that for likelihood ratio tests. We could compare models with it. The AIC listed right here, 552.51, is used for non-nested model comparisons, right? So likelihood ratios, nested model comparisons, non-nested models are AIC. Okay, so the coefficients from each for each form of the model, right? Beta 0 is our intercept that's in logits. If we just raise the constant e, Euler's constant, to beta 0, we get the odds back actually, which is really cool. So we have odds. So the e to the our intercept estimate is 0.819, saying the average odds of applying to grad school, 0.819. And then our probability itself is e to the parameter over 1 plus e to the parameter itself, right? So the average probability of applying is 0.55. Not bad. All right, moving forward. We can talk about maximum likelihood estimation as well. Similarly, I don't have to dwell too much on this, but basically we're maximizing the likelihood function. But instead of where we built a likelihood function using a normal distribution, now our PDF that we use is Bernoulli. And here, the key is in the likelihood function, we have our parameter for the mean. We just need to, instead of having the mean there, we insert our link transformed linear predictor where we see our mean. So it makes the math a little bit more ugly, right? We have our link transform linear predictor in each of these spots, but that's our likelihood function. This is our sample likelihood. And now we can do a little log of it to build the log likelihood itself, do a little algebra. And we can see that here, if we varied values of beta 0, we could find its height. And that height of that likelihood, the peak of it, is our maximum likelihood estimate. So here is what I ended up doing, right here. And we can see this value of the mean happens to be its height itself. So why I dwelled upon maximum likelihood is to get you this point. Every distribution has a distribution. Every statistical distribution has a PDF, sometimes called PMF. We can use those to build a sample likelihood as a function of our parameters of interest. And then we search for the parameters that give us the maximum. So why I say, hey, if your data don't transform your data, change your distribution, change your model, is because we literally can use maximum likelihood in any case, so long as we have a distribution that we work with. And we always are going to. So that's why I dwell on that. So this is the history. This comes from the CLM control. You can see where the value is. The iteration, so it started with a parameter value of 0, and then using Newton-Raphson, gradients those are partial derivatives themselves. It worked its way in 3 different steps to a parameter, well, in 2 steps it got there. The third iteration, it got 0.2007, and just to check that it was in the right spot, it did another iteration, and it saw that there's very little difference between these 2 steps, so it converged numerically there. So rather than doing this grid search where I tried out values all around, it only did basically 4 different steps to figure out, hey, we are at the right location itself. What you can see is, as it's trying this, the parameter of 0, which you see is right here, there's your first log likelihood. And then from there, it guessed parameter of 0.2 right there. And actually, remember, these parameters are on the other side. This is actually negative 0.2. So it got closer. So it went right here, then it went right here, then it went there. So it's basically jumping over. All right, at the maximum, we now assume the distribution of the parameter is normal. We assume asymptotic convergence, just like we saw in the maximum likelihood lecture. So that means that beta 0, we thought, thinks follows a normal distribution where the mean of it is its point estimate, and there's a standard error, or the variance of it is its standard error squared. And we can use this feature later on to assess the significance of each of our parameters. But what you're noting here is this significance looks like the coefficients table. If you were to try to get a sums of squares table, you wouldn't get it out of this because we're not in a least squares approach. We are in a maximum likelihood approach that we go and build wald tests to determine whether our parameters are significant. Right? A wald test for the intercept, which really doesn't mean anything in this case, but be beta 0 hat over the standard error of beta 0 hat. That gives us our test statistic, and we compare that thing versus a normal distribution with a mean of 0 and a standard deviation of 1. All right, let's add predictors to our empty model. Having examined how the logistic link function works, let's do this. Let's add parental education as a predictor. Let's set our GPA at 3 and add it as a predictor, and add whether or not a person's at a public university. So if this were what you saw, you'd think, oh, I'm predicting is a regular regression line almost. However, the left-hand side of this is the logit of the probability of a person saying they're interested in applying to grad school. Right, so when we plug that in, if we think about this, this is the link version. The G inverse of it looks like this: e to all those terms over 1 plus e to all those terms. But always the variance is at p times 1 minus p. For now, we're going to omit interactions to simplify the interpretation, but I will go on later and try to add those. And we're also going to use the default parameterization. So we're now modeling the probability of a 0, not the probability of 1. So this probability is now the probability a person is not applying to grad school. This is the other thing when it comes to generalized models for categorical outcomes. Modeling the probability of 0 is roughly equivalent to modeling the probability of a 1. It just changes the sign of each of the parameters involved. All right, so here, the CLM formula, we just put our variables in. Each of these are specific names that have to appear as variable names in the data01 data frame in R. Again, you can see the trace of the iteration history. It tried out all zeros for the original guess of the parameters, and then those parameters wiggle around slightly until it ended up converging right here after 3 steps. So the first question we want to know is, does this model fit better than the empty model? That's like saying, hey, are all the regression coefficients simultaneously equal to 0? Because if they were all equal to 0, we would get the empty model. So this is our null hypothesis we're testing. We can use the ANOVA statement to do it. Now, don't let ANOVA fool you. This is a likelihood ratio test, but ANOVA is what we call a generic primitive function in R. So it's what we use to make model comparisons. Here we can see the log likelihood from the original model, the log likelihood of our model. -2 times the difference is 20.586. This is compared to a chi-square distribution with 3 degrees of freedom. The degrees of freedom are the difference in model parameters. We had 1 in the empty model. We have 4 in this model, so 3 is that value. You can see that the degrees of freedom are 3 here. The p-value is very, very tiny, meaning that we would reject this null hypothesis. And because this is a 3-parameter null hypothesis, we'd say at least one of those values is not equal to 0. Now, which one we'd have to go and follow up with looking at each coefficient, which is what we'll do next. So here we put our summary statement in R, and we see that the slope for parental education has a p-value less than 0.05, and the slope for GPA3 is slightly less than 0.05. So we'd say both of these are statistically different from 0. Right? We'd also see that the public value right here, this thing, is not significant necessarily. Right? So it doesn't really matter whether or not a person goes to a public or private university. Right? So the intercept, or in this case, the threshold, is the predicted probability for the logit of 1. If we take the threshold is for a 0, but if we convert that to intercept, we multiply it by -1 itself, right? So we can interpret the model parameters. Parent right here is whether one of the parents had a graduate degree. This is a 0-1 variable, right? So this is the change in logit for every 1 unit change in whether a person has a parent with a graduate degree. But you know that A 1 unit change means going from a 0 to a 1. So basically, it's the difference in logits between someone with a parent and with a graduate degree and someone without. So that is it. It means, so because of the logit y means a rating of likely to apply, this means that students who have a parent with a graduate degree are more likely to rate the item with a likely to apply, right? The logit goes up, so the probability goes up. Now, how much, the quantification of how much less likely or how much more likely a student is to respond with an unlikely to apply can be done using odds ratios or probabilities, right? We could have taken the odds ratio of likely to apply for a student with a parent degree or a student without a parental degree, and we could see their ratio, right? Their ratio happens to be 2.88, meaning a student with a parental degree is almost 3 times the odds of rating likely to apply. Odds ratio show up a lot in medical studies. You can see this when it comes to drug trials, other places as well. I don't like thinking in odds, like saying someone is 3 more times likely to apply sometimes forgets the magnitude, particularly for rare diseases, right? The odds of, dying due to having one cigarette is much higher than not, but both are fairly small, hopefully. And it's the 20 or well, let's not get into that. I'll leave that example. But let's convert it into probabilities. The probability of someone who's likely to apply for a student with a parental degree is the sum of those two parameters, or 67% chance of applying, or probability they apply, likely to apply. But if they don't have a parental degree, it drops down to 0.416. Probabilities are nice because they do see the scale itself. But odds ratios, these are where we define effect size for. Now, we could also look at the public value here. This is whether or not a person goes to a public university. This is not significantly different from 0. This basically means that a person who is there's no difference in likeliness of to apply. Now we can talk a little bit more about so the quantification of how much more likely a student is to respond with likely to apply can be done with, again, odds ratios or probabilities. We can form the logits for each. We can take their odds, or we can take their probabilities. But let's look at GPA. It's a quantitative variable and continuous, right? So for every 1 additional unit of GPA, the logit of likely to apply goes up by 0.5482. And so because the logit goes up, this means that students who have a higher GPA are more likely to rate likely to apply. And this is where we can really look at an odds ratio as being helpful, right? So how much more likely? So here's our logit. If we plug in GPA 3 right here, we can get our logit for each value that associates to it. We could take the e to that logit and get an odds ratio, or we could see the GPA as well. Now remember, GPA is centered at 3. So this GPA 3 of 1 is really a 4.0 GPA. So their probability is 0.552, and you can see it decreases as a function of how that GPA goes down. Okay. Odds are found by just plugging in those values. The probability is found by plugging in these values. Now, I should note that this is for someone who's has 0 for all the other predictors as well, but just to kind of demonstrate how it works. And we can also plot this, right? It's an unconditional main effect, so we can plot it for values of GPA versus probability. These are probabilities, right? So as GPA goes up, the probability of likely to apply goes up. But if the probability of likely to apply goes up, that means the complement, the other probability, 1 minus it, must come down. So in general, the linear model interpretation that you've worked on to this point still applies for generalized models, but with a little bit of nuances, right? So all the regression coefficients are now for logits, and the direction of what's being modeled has to be understood. Y of 0, y is 1, right? And if you notice here, this really applies to the intercept. And the change in odds and probability is not linear per unit change in the intended variable, but it's linear with respect to the logit. That's why we have to go back to probabilities to talk about how a change in GPA, for instance, changes probabilities. Now, that's all main effects. Guess what? If we put interactions in, they're still going to work the same. They're going to modify the conditional main effects, and simple main effects are conditional main effects when the interacting variables are set to 0. Those are the parameters of the model. So to wrap up, this was a quick introduction to generalized linear models, particularly through logistic regression. It's not meant to give you all that you need to know, but it's meant to get you started as it goes. The estimation process is largely the same. Maximum likelihood um, is still the gold standard as it provides estimates with understandable um, properties, good properties. And learning about each type of distribution and link takes time. There are entire books written on how to model count data, for instance. It's really complicated, but that's great. Knowing about it is the first step. The other part that's also nice about this, if you combine maximum likelihood or perhaps even Bayesian, there's really no way, no software that could keep you from doing a model that's specific to the type of data you have, even if you have to do a little bit of work to define it. So logistic regression is one of the more frequently used generalized models. It's often introduced in a regression class outside of the whole framework of generalized because it is somewhat complicated to think about. But I want you to think about both. You can do logistic regression, but you can also work more generally. All right, that's it for me. Thank you for listening.